Geometry, Chapter 6, Lesson 6, and in this lesson we want to take what we've learned about these quadrilaterals that we've been dealing with and all of those characteristics, and then also take a look at the coordinate plane and looking at formulas that we've done before, slope formula and distance formula, and kind of tie those together into something that is called coordinate proofs, which we'll look at in the next lesson. And you remember when we did these special parallelograms and we had the coordinates and we placed those figures in the coordinate plane, and then we used the slope formula to determine if the slopes of the opposite sides were the same, because then they were parallel. And we could use then the slopes, and if the slopes were negative reciprocals, then the sides are perpendicular. And we used the lengths of the distance formula to determine if the lengths were the same, if we were trying to figure out if the figure was a rhombus or an isosceles trapezoid perhaps. Now in this lesson we're going to do much of the same things. However, the coordinates aren't going to be numbers, they're going to be letters. Because in many instances we may not know what the exact length of a side is, we may not know what the exact coordinates are as far as in terms of a number. However, the power of mathematics is being able to take something that's concrete like a number and to go from the concrete to the abstract, meaning we go from the number 4 and instead of 4 we put in something that's not so concrete and we put in the letter a variable. So now that letter A can be different things, so it's not as concrete as it was before. However, the power of having something that's abstract in that manner allows us to apply it to multiple different scenarios, whereas before, if we were using the number 4, we could only use that if the length was 4. If it was another length, we couldn't use it. If it's a variable, we can use it for a length of 4, a length of 12, a length of 7, a length of 15, it doesn't matter. So there's great power that comes from mathematics, from going from the concrete to the abstract, and that's really where the power of mathematics lies. So what we want to understand is that whatever we can do with numbers, the concrete of math, we can do with letters, more abstract. The only difference is the letters don't allow us to sometimes get an answer into a nice, neat little one number package that we're used to. So we just go as far as we can and then we stop. So we're going to take 2 lessons to kind of do this. The first thing we're going to do is take a look at how do we place a figure in the coordinate plane, and then how do we name the coordinates. And then in the next lesson we'll look at then actually using those coordinates maybe to prove some things. So let's look at naming coordinates. Now, when you're working with a figure in the coordinate plane, it is generally a good practice to place a vertex at the origin and then one of the sides along the x-axis. Then when we name the coordinates or the vertices, we want to use multiples of 2. And the reason we want to use multiples of 2 is because if you think about our midpoint formula, we have to divide by 2. x1 plus x2 divided by 2. If we're using multiples of 2, we're always going to get a nice even number. If we're using odd numbers, or just like the letter A or 1a, which that actually represents, when we divide by 2 we have a fraction. So by using multiples of 2, it helps us when we have to calculate midpoints that we don't end up with fractions. The reason we want to place it at the origin is because we already know what the coordinate of the origin is. The coordinate of the origin is 0, 0. So by doing that, we then have one of the coordinates of the vertices, and then we just need to name the other 3. Now when we're naming the other coordinates, we want to remember that if we're moving horizontally, those are my x values, or my lengths. If we're moving up and down, those are my y values, those are vertical. And if we remember that the characteristics of these figures, like the opposite sides are the same, or you know, the diagonals are equal, or sides are perpendicular, then we can write these coordinates fairly easily. So I think the best way to tackle this is to do a few problems and to name some coordinates while we're at it. So let's take this. Let's take a simple figure like the square to begin with. Now, we said that it's good to place one vertex at the origin. So if I place the square at the origin and then one of the sides along the x-axis, I can then name these coordinates pretty easily because, let me adjust my pen here. Well, we already know that this coordinate here is the coordinate 0, 0 because that's the origin, so that's why we wanted to name it there, or to place it there. Now, we want to name this coordinate. Now, how far is it from here to here? We don't know, but whenever we don't know something, we can always give it a variable. So let's say the length of this is a. If that's the case, then what would be this coordinate right here? Well, remember, this coordinate is the distance horizontally, so the x value, so to speak, would be a. And then vertically, I don't go up or down, so it would be 0. So the coordinate of this point would be a 0, a representing the horizontal length. Now, what would be the coordinate of this point? Well, again, horizontally, I don't go either way, so that remains 0. Now, because this is a square, all the sides are the same length. So if this horizontal distance is a, what will be this vertical distance? A. So the coordinate of this point would be 0a. And then the coordinate of this point would be, well, if I'm going this far this direction, how far is that? That's a. And then I'm going this far this direction, which is going to match this, so AA will be my coordinates. Now, I got so excited about doing this one figure that I totally forgot the second thing that we said was a good thing to do. Do you remember what it was? We want to use what? Multiples of 2. So, because if I'm going to have to determine the midpoint, I want to have multiples of 2. So, rather than making this distance of a, let's just make it 2a. So that doesn't do much but change this from a to 2a, and then the other value is still 0. Now, because that is 2a and because this is a square, that's just going to change this length is 2a because this length is 2a as well. And then I could change this point, so the distance from here to here is 2a. And the distance from here to here is 2a, so the coordinate of that would be 2a. So I can label all these coordinates with some variables, and then I'm able to use slope formula or distance formula or even midpoint formula, because all I have to do is take the y value, for instance, the slope formula, this y value minus this y value over this x value minus this x value, and I can determine the slope. Okay, let's do another figure like this rectangle. And let's try to remember to use multiples of 2 this time. Alright, so if I place this here, again, I already know this point here is 0, 0. That's the advantage of using the origin. Now, this length I don't know, so let's say that this length is 2a. So again, I can determine the length of this is 2a, and then 0, that would be the coordinate. Now this point, now this is not a rectangle. I mean, sorry, this is not a square. So this side is not going to be the same as this one. So this is a different length than this. So I can't use A because I already have A used up here, so I'm going to have to use a different letter. So let's call this B, but again we'll use multiples of 2. So let's call this then length, distance from here to here, 2B. Okay, so this length is 2B, this length is 2A. Now I can determine the coordinate of this point by taking the length of this side, 2a from the origin, and then I go up how far? 2b, so I can list the coordinates in that way, and then again now I have some coordinates where I could use those other formulas that I'm used to using. Let's say sometimes we can center the figures at the origin rather than putting one at the origin. In other words, rather than putting this figure here, I could put the figure centered right here. So these lines would go through the center of this square. Now, if this entire length is 2a, then the distance from here to here is only going to be a. Now again, I want multiples of 2, so I want the distance from here to here to be 2a. So if this is 2a, okay, so this would be 2a this way, and then this would be then 2a up because it's a square. And then this would be over 2a, and then because I'm going down, it'd be negative 2a. And then this one would be negative 2a, and then going up 2a. And then this would be negative 2a, and then this would be down negative 2a. So if we center the figure on the coordinate plane, we can still use multiples of 2, and we can still label the coordinates. Now another thing you might want to do is take a figure like this. Now you can't put a vertex at the origin and then one side along the x-axis. So in this case, centering it along the origin is going to be a little bit more valuable to us. And then because these bisect each other, then this length from here to here, let's say, is 2a. So that's going to be 2a, 0, and then the length this way would be the same because it's bisected. This is a different length, so we'll call that b, so it would be 0 and then up to b. And then I have 0, and then I can go down 2b, so negative 2b. So again, by centering the figure, that may make things a little bit easier for me. Now again, the reason we want to do this is because once we have a figure in the coordinate plane, we can then apply the formulas that we've learned before in order to determine the slopes, which would help us determine if the sides are parallel or perpendicular. We could determine the midpoint, which we'll have to do because we know that the diagonals bisect each other, or they're supposed to if they're in a square or a rectangle or a rhombus. So we would want to calculate the midpoint to ensure or to show that they are actually cutting each other in half, and we may need to determine the lengths using the distance formula in order to calculate those. So we need coordinates in order to use these formulas, so placing the figure in the coordinate plane and then assigning coordinates to it using multiples of 2, we are then able to use these formulas to calculate different things that we may want to calculate in order to prove that the figure is a certain shape. So for instance, let's look at number 2 here. It says to give the coordinate points, or 4 points, w and z, without using any new variables. In other words, they give me the coordinate of this point right here as b, h, and then I need to give the coordinate of w and z. Now, the important thing to remember is this x value is the horizontal distance, and this y value is the vertical distance, so I can use that. Plus the fact that I know that opposite sides of a parallelogram or of a rectangle are congruent, and I'll be able to write the coordinates in that way. So the coordinate of this point, the distance from here to here, is going to be the same as the distance from here to here, and that's given by the x value. So I know that the length of this is going to be b, and then I don't go up and down, so that's 0. So the coordinate of z would be b0. The coordinate of w is the distance from here to here. The vertical height is the same as the vertical height of this side, so this y value would give me the coordinate of this. So I don't go horizontally at all, but I do go up h. So that would be the coordinates of the points w and z. And that's all you'll need to do on these particular diagrams. Let's take a look at number 5 here, because this one's kind of interesting. It's a parallelogram, so I know that the opposite sides are the same length. That's one of the characteristics of a parallelogram. Now, what I know is, because of this coordinate here, that the distance from here all the way to here is c, because that's why this is c. In order to figure out z, I need to know what this is, because that's the distance from the origin to here. Well, one way to look at this is the length of this side from here to here is the x value of this coordinate, so this is c minus a. So because opposite sides in a parallelogram are equal, that means this is c minus a as well. So what I need to know then is, if from here to here is c minus a, I need to add something, this distance from here to here, whatever that be, so that this distance is equal to c. So what could I put in here that would make this equal to c? Well, if this was negative a, if I added the opposite of that, or a minus a is 0, which would leave me c is equal to c. That means the distance from here to here must be a. So now that I have that, I can write my coordinates, because the coordinate of z is this distance here, which is a, and then 0. And then w is simply 0, and then the height is going to be the same, which will be the y coordinate here. So 0b would be the value of w. Okay? So by placing these figures in the coordinate plane, we're able to write the coordinates even though we don't know the exact values by placing them in that way. Let's do one more. Let's look at number 7 real quickly. Here is v and here is w. They give me all these distances here. So this from here to here is a, and this from here to here is a, just in the negative direction, neither up or down. Now because it's placed in the center, then z is going to be half of this, or it's going to be this height right here, which is c. So that would be this. Now, because this distance is b, this is going to be b, the same length, just in the opposite direction. And then the height is going to be the same height as this, which would be c. So by placing those figures in the plane and by looking at the coordinates given to us, we're able to determine the coordinates of the point without using any new variables. We're just going to have to use the variables that they use and do a little bit of reasoning based upon what we know about these figures.